Fundamental theorem of calculus. Essential question. Can you follow the proof of the fundamental theorem of calculus? Before we start, let's talk about the mean value theorem. The mean value theorem says that as long as a function is continuous and differentiable, there exists a value at which the instantaneous rate of change is equal to the average rate of change. Now, the average rate of change is the slope from one endpoint to the other endpoint of the interval, the end of the interval, and that is the slope. An instantaneous rate of change will be the slope at a particular point, and they'll be equal to each other. So they will be parallel or the same value. Now, this is the way it looks graphically. The way it looks analytically is this. We go ahead and use the interval to help us find the average rate of change, and this is the average rate of change right here. And we're looking for at what x will the instantaneous rate of change be equal to that. So we take the function, take its derivative, set the derivative equal to the value of the average rate of change, which happens to be -1, solve for x, and we get 4.5. So at 4.5, the slope at 4.5 will be equal to the average rate of change in the interval from 3 to 6. Keep this in mind as we go through the proof. Okay, so we want to prove that a definite integral can be calculated exactly using an indefinite integral. We want to write the definition of this integral, and that definition is this. It represents the limit as n approaches infinity of the summation of I equal to 1 to n of f of c sub I times delta x, so the sum of all the rectangles. This is called net area. Oh, okay, we want to write the definition of this, and this definition, remember the word that should come is antiderivative. So g of x is equal to this antiderivative if and only if g prime of x is equal to f of x. So this right here is the derivative. Now, how can you be sure that the mean value theorem applies to the function g? Well, here are the requirements. G has to be differentiable on the interval from a to b. G is continuous on the interval, the closed interval from a to b. And because we have differentiability, that implies continuity. All right, let's take a look at this figure, and we want to write the conclusion of the mean value theorem as it applies to just this interval. And so the instantaneous rate of change at some value, we'll call it c sub 1, is equal to the average rate of change in the interval, and that's going to be g of x sub 1 minus g of a all over the difference in the x's, x sub 1 minus a. Okay, now what we're going to do within a whole interval, and we are going to have various points here. So we want to write a Riemann sum, r sub n, for this integral, and we want to use sample points, and what's important here, we want equal delta x values. That's a requirement. So here's our c sub 1, and that's going to create a height, and that'll be the height of this rectangle. So the height times the width. And then we're going to use another point in the second interval, f of c sub 2 times the width, and so on. So all of these f's are the heights of the rectangles, and the difference in these x's are the widths. Now, since we have equal values, we can write these as just delta x, and that's what we have here. I'm going to factor out a delta x, and we'll just have the sum of these heights. So these are all, this represents here f of c sub 1, this represents f of c sub 2, and so on. Okay, well these heights here that we said were f of c sub 1 and f of c sub 2, remember that this is a derivative curve. We're trying to find the area under a derivative curve. So f is actually the derivative of g. So I am going to substitute right here. I'm going to substitute g prime of c sub 1 for all the f's. So now all the f's have been substituted with g prime. And these are representing, there should be a dot dot here. These all represent the derivatives, and here's our delta x. Now remember, the definition of derivative is going to be, well, no, not the derivative, but we know this instantaneous rate of change is equal to some average rate of change in the interval. So I'm going to now take all of these instantaneous rates of change and substitute the average rate of change. So that's what we have here, here, and here. And then we again times by delta x. Now all these denominators are going to cancel. Let's see. We're going to reduce here, and we're going to just get these numerators, g of x sub 1 minus g of a plus, and so on, so on, so on. And there's going to be kind of a domino effect in that things are going to get canceled. Somehow we reuse another g point here. Now there is no canceling of this one because this doesn't get used again, nor will there be a canceling of this one. So in the end we are going to, this is, I'll write g of b minus g of a instead of writing it the other way around. So this comes down to g of b minus g of a, where g represents the antiderivative. All right, let's take a look at how the r sub n is independent of n, the number of increments, and we're going to use this fact. This, remember, is the Riemann sum with n, and we're going to have, it's going to be between a lower n where we only choose the smallest heights in every interval, and the Riemann sum with the upper or the highest y value in the small little intervals. Now remember that we have concluded that this Riemann sum amounts to this, and it's between this lower and upper. Now I'm going to increase accuracy by taking the limit of all three here, and this limit right here actually becomes the area under the curve, and so does this, because the intervals become smaller and smaller and you have bigger and bigger accuracy. So the squeeze theorem shows that this is going to be caught between these two intervals, which are exactly the same. So what we can say is, the conclusion is, we can say that the integral from a to b of f of x dx, that area under the curve, will be the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. And that's what this is saying. This is huge. Double star, triple star. Okay, so how does that look in an example? All right, so I want to find the area from 1 to 4 of x to the 1/2 power dx. And so the conclusion of the fundamental theorem of calculus says if you can find the antiderivative, and we can, so this is going to be 2/3 x to the 3/2 power. Now check your work and make sure that when you take this derivative you get back to here, and we want to evaluate it from 1 to 4, and this symbol here says I'm about to evaluate it. So I want to take this antiderivative and evaluate it at the upper limit, which is 2/3 4 to the 3/2 power minus, I'm going to take this antiderivative and evaluate it at the lower limit, and then we're going to get 16/3 minus 2/3, and we end up getting 14/3. Now I would ask you to go to RAM, one of your RAM formulas, and go ahead and put it in here, put for 50 rectangles, and see how the approximation using RAM is approaching this exact answer.